Hi everyone, in this video we're going to learn how to solve an exponential equation, which as we're about to see involves a hidden quadratic equation, for which we'll need to find a range of values of a number k, such that the equation has at least one real solution. So let's get started. The question reads as follows. Find the range of possible values of k such that the equation e to the power of 2x plus ln of k, which equals to 4 times e to the power of x, has at least one real solution. Okay, well, as I always do, let me start by writing SOL here for solution. And I'll also copy the equation. So that's e to the power of 2x, or e to the 2x, plus ln of k, which equals to 4e of x. Now, looking at the equation we have here, the key thing to notice, or to draw one's attention towards, is the fact that this exponential is e to the 2x, and the other is e to the x. We could also say that this is e to the power of 2x, and this one is e to the power of x. And when faced with two exponentials like this, that is, when the exponent on one is 2 times the exponent of the other, it's often a good idea to remind ourselves of the fact that e to the power of 2x, or e to the 2x, is equal to e of x squared. Indeed, this is often helpful as it will allow us to pick up on any quadratic pattern in this equation. In fact, in my classes, what I tell my students is to go as far as giving e to the x a different name. That is, we'll define a new variable. And what we usually do is we say, let capital X, so it's a different x, equal to e of x. And in fact, let me go ahead and box that, like so, and now I'll show you how I would use this in this equation. Replacing this e of x by capital X, and this e of 2x, which would therefore be capital X squared, this equation turns into capital X squared plus ln of k, which equals to 4 capital X. In other words, 4 times capital X. And looking at this equation now, it's perfectly clear that we're dealing with a quadratic. And so the next step really is to gather all the terms on the same side of the equation, so that it turns into capital X squared minus 4 capital X plus ln of k equals to 0. And in fact, I'll go ahead and box that equation. There we go. Now let me say, we don't have to do this. In other words, we don't have to write e of x equals to capital X and rewrite the equation this way. Indeed, if you're comfortable with saying that this is e of x squared minus 4 times e of x plus ln of k equals 0, then by all means write things that way. I simply find that by rewriting the equation thanks to this change of variable, it allows me to at least temporarily forget that I'm dealing with an exponential equation and focus solely on this quadratic equation. That being said, I carry on. Remember, we need to find the range of possible values of k such that this equation, which is the same as this one, has at least one real solution. In fact, I'll go ahead and box that. And the important thing to remember here is that a quadratic equation will have at least one real solution provided its discriminant delta is greater than or equal to 0. And in fact, let me write that. This quadratic equation will have at least one real solution if and only if its discriminant delta is greater than or equal to 0. And we could be more specific. If delta is equal to 0, then this equation will have exactly one real solution. And if delta is greater than 0, then this equation will have two distinct, meaning different, real solutions. And remember, for the generic quadratic, so ax squared plus bx plus c, the discriminant delta is given by the formula b squared minus 4ac. And so for the quadratic equation we've boxed here, the coefficient a will equal to 1, b will be equal to negative 4, and c will be equal to ln of k. And so replacing b, a, and c by their respective values inside this formula for delta, we find that delta is equal to negative 4 in parentheses squared minus 4 times 1 times ln of k. Now, negative 4 in parentheses squared, well, that's equal to 16. And so that's 16 minus 4 times 1 times ln of k, so that's 16 minus 4 ln of k. And there we go, that's delta. And in fact, I'll go ahead and box that like so. Okay, carrying on with the working over here. Remember, for this equation to have at least one real solution, we need to have delta greater than or equal to 0, which means that this expression, 16 minus 4 ln of k, has to be greater than or equal to 0. And so I'll go ahead and write that 16 minus 4 times ln of k has to be greater than or equal to 0. And now all we need to do is solve this inequality in terms of k. So let's go ahead. The first thing I'll do here is I'll add 4 ln of k to both sides of this inequality. And I suppose I could write the steps here, so I'll add 4 ln of k to both sides, like so. So this becomes 16 is greater than or equal to 4 times ln of k. Next, I'll get rid of the 4 that's multiplying ln of k, and I do so by dividing both sides of this inequality by 4. And so again, I'll quickly write that. I'll divide both sides by 4. And so we get 16 divided by 4, which is 4, greater than or equal to 4 ln of k divided by 4, which is just ln of k. And at this stage, I like to write this in such a way that the ln of k appears on the left-hand side of the inequality, and so I can simply rewrite this as ln of k must be less than or equal to 4. We're nearly there. I'll carry on at the top here, and I'll just copy that last result. We have ln of k that's less than or equal to 4, and consequently, we can state that k must be less than or equal to e to the power of 4. And careful, although it's tempting to stop here, because indeed it looks as though we've found the range of values of k for which this equation has at least one real solution, we're not quite done. And here's why. It's very important here to keep in mind that k is the input value inside this ln function. And this is important because the ln function, like all log functions, is only defined for positive inputs. In other words, just based on the fact that we have ln of k, we can already state that k had to be greater than 0. And so keeping this result in mind, alongside the result we just found, to get full marks at this question, we'd have to say that k has to be greater than 0 and less than or equal to e to the power of 4. And that's the final answer. Indeed, provided k is greater than 0 and less than or equal to e to the power of 4, the equation we have here will have at least one real solution. And as such, we've answered the question. Now to finish, although this wasn't asked in this question, and so wouldn't be required in your answer at an exam, let me go a little further here. And so I'll just quickly write extra here, like this. There we go, this is extra. Again, what I'm about to write is not required for you to get full points at this question. For values of k that lie between 0 and e to the power of 4, not including e to the power of 4, and so I'll just write that here. If k lies between 0 and e to the power of 4, not including e to the power of 4, then the delta we have here will be greater than 0. Indeed, you can go ahead and check, but in the expression we have for delta here, if k is less than e to the power of 4, then this 4 ln of k will be less than 16. And so delta will be greater than 0. And so let me just go ahead and say, if k lies between 0 and e to the power of 4, then that will imply that delta is greater than 0. And in that case, this quadratic equation will have two solutions. And so we could say that we'll find that capital X equals to P, and that capital X equals to Q, those being two distinct real solutions. Following that, remembering that capital X was e to the x, we'd rewrite those two equations as e to the x equals to P, and e to the x equals to Q. And we'd quickly solve these using the natural logarithm, and we could quickly state that the x, that's lowercase x, is either equal to ln of P, or it's equal to ln of Q. And those would be the two types of solutions that we'd get if k lies between 0 and e to the power of 4. And in fact, I'll underline that here. There we go. And I'll put a little bullet point, like so. On the other hand, if ever we had k equals to e to the power of 4, well, in this case, looking back at our expression for delta again, if k is equal to e to the power of 4, This 4 ln of k becomes 4 ln of e to the power 4, so that's 4 times 4, which is 16. And so we'll have delta equals to 16 minus 16, which is 0. And so I'll quickly write that here. This would imply that delta is equal to 0. And so the quadratic equation we have here will have one single real solution, which we often call a double root. And so we could say that capital X in that case would equal to some number, which I'll go ahead and call r. And finally, since capital X equals to e of x, we could go ahead and state that e of x equals to r, and so x, that's lowercase x again, would equal to ln of r. And that would be the type of solution we get. And there we have it. That's how to solve this exponential equation involving a hidden quadratic equation, for which we had to find a range of possible values of k such that it had at least one real solution. There we go, everyone. I really hope that helped, and if it did, please hit like on this video, drop a comment down below, and even subscribe to this channel to help get this video to as many students as possible. All that being said and done, that's it for this tutorial.